This little topic is about carboxylic acids, its nomenclature and properties. Carboxylic acids is actually a huge chapter and a huge functional group also for that matter, but in this one we'll just focus on the acids. So carboxylic acids are RCOOH, where R can be hydrogen or any other function or any other alkyl or aromatic derivative. So that's carboxylic acid. You have to have COOH in there. Carboxylic acid as such is a terminal group, which means that you can find it only at the end somewhere. You will see it clearly. Carboxylic acids have a lot of derivatives, esters, amides, and are all the lists, okay, for all the derivatives that we'll be studying. So for example, here's the acyl chloride, the anhydride, okay, which has all of this. Ester, which you know of already, you learn about those when you learn about your functional groups. Then nitriles are the C double triple bond N. And then we have the amides, and the amides are written over here as separate because you can have NH2 or you can have NH2 as in the hydrogen substituted with different alkyl groups as well. Okay, and so that would give you different kinds of amides. The only functional group here, the derivative only here that does not have the carbonyl functional group is the nitrile. Okay, all the other ones you can clearly see the C double bond O, but nitrile is a little bit unusual, and that's fine. Okay, it doesn't matter so long you recognize that it is a carboxylic acid functional group. Okay, so that's nitriles. Let's talk about the nomenclature then. For most of the part, the names will end in oic acid. Okay, so it's kind of easy to know that you're talking about carboxylic acid because everything is ending in acids. So one of the things about carboxylic acid is that they are the highest priority group. Okay, and that's something that we'll have to remember as we go on with the nomenclature. The other thing about carboxylic acids that is not so unusual is that they do have a lot of common names. Carboxylic acids have been around for a long time, and so a lot of them have common names, okay? And so as we go on, we'll learn about those also. And I will mention to you which ones are going to be required of you to know and which ones are not, okay? Because there's so many names, how can you remember all of them? So anyhow, here is the first carboxylic acid, which is with one carbon, and there's a hydrogen over here. The IUPAC name for this one is methanoic acid, again the meth coming from the one carbon, and then oic acid. The general name for this is formic acid. And if you think back to what we did with the aldehydes and ketones, you remember we talked about formaldehyde. So the form actually has to do with the one carbon, okay? And then of course the second carbon, add one more carbon to it, and we have ethanoic acid or acetic acid, and acetic acid you know quite a lot. With 3 carbons is propanoic acid, and the general name for this is propionic acid. Yes, it's a very small difference, so do not ignore that, okay? Propanoic acid versus propionic acid. And then the 4 carbon is butanoic acid or butyric acid, and the other acid that you are familiar with so far is benzoic acid, okay, which is with a benzene ring. So for the naming, if you have larger structures, then you will start the numbering from carboxylic acids. That's the highest priority group. And then you will number to the longest chain, okay, as usual. And so in this case, 5 is the longest chain over here, so that's pentanoic acid. And on the 4th carbon, there is a methyl group. So that's 4-methyl pentanoic acid. Here you have a double bond, and so the longest chain is 6 carbons. 1 is, of course, the acid, so you don't have to count that. But the 4th carbon, there is an ene. A double bond, so this becomes 4-hexenoic acid. Okay, and so the 4-hexene, the 4 tells you that there is something on the 4th, and the ene, of course, stands for the alkene. So this is another way of naming it. This is the current way of naming it, okay? Hex 4-enoic acid. So in the new system, remember we place the number right before what the functional group is. Okay, so here the functional group is on the 4th, and it's ene. This structure here, this is a diacid now, okay? And so there is an acid here, there is an acid over here. Remember, acids are terminal groups, so you'll usually find them at the end, okay? And so this is an 8-carbon structure, so this is octane. You have 2 acids, so this is a dioic acid. And then you will start numbering from wherever it's closer to the chain, which in this case, both of them are. So 1, 2, 3. 1, 2, 3. So then you go alphabetical. Okay, and so 1, 2, 3. Ethyl is alphabetically lower than methyl group. Okay, so 3-ethyl, 6-methyl, octane, dioic acid. If you have cyclic compounds, and I don't think you will encounter that many cyclic compounds, but if you do, then the carboxylic acid is used as a substituent, okay? And then you always go start the numbering from where the carboxylic acid is. So this is a cyclohexane, so cyclohexane and then carboxylic acid and whatever else is attached to it, okay? So on the 4th carbon, there is a hydroxy group. So this becomes 4-hydroxy cyclohexane carboxylic acid. Yeah, lovely name. And in any case, in this case, there is a stereochemistry given to you, so then you have to mention that also, okay? Trans in this case. Here is one with the cyclopentene ring, so cyclopentene, and then you have to say the carboxylic acid and give the location of where the double bond is, which is on 1. And remember, your numbering will start from where the carboxylic acid is. So there are a whole bunch of diacids, okay? In the previous slide, you saw a diacid, but diacid is actually more common than that. And you have 2 acids and, of course, 1 group. And usually what happens is that you use their common name a lot more than their IUPAC name, okay? Because they've been around for so long and we use them so often. So, for example, with just 2 carbons, okay, carboxylic acids on each of the carbons, it's called oxalic acid with 1 CH2 in the middle, so we are increasing CH2s over here. It's called malonic acid, and the succeeding glutaric. Adipic acid is when you have 6 carbons, maleic acid, and so on and so forth, okay? And so it gets to be a lot of names here. Now, usually you will not have to memorize any of these names. If the name is given to you, hopefully the structure will be given to you as well, okay? So don't try to memorize this. Maybe it will come to you if you look at it often enough, but no need to memorize it. Not for me. The physical properties of carboxylic acids, the boiling points are going to be high because there is hydrogen bonding as well as dipole forces. Okay, so the OH group in there, of course, is responsible for the hydrogen bonding. 2 oxygens in there, okay, are for the dipole forces, especially the carbonyl oxygen, okay, that is polar. All carboxylic acids are going to be liquids because of that reason. So even methanoic acid is a liquid and it is of high boiling point, all right? And the physical properties are given in the next slide as we'll go over, okay, in just a minute. So as the number of carbons increases, the boiling point also will increase. Now the diacids will of course have a higher boiling point than monoacids because they have 2 acid groups, okay? Obviously. So then the solubility also, most of the acids are going to be soluble in water because of the hydrogen bonding forces, and then of course the dipole forces, okay? And then solubility decreases with molecular weight because then you have more of the carbon in there, so more of non-polarity goes in there. So the smaller ones like acetic acid, methanoic acid, they're completely soluble in water, no problems. And again, diacids will be more soluble in water than the monoacids will be. Most of the acids are going to be pungent in smell, which means you can know that there is an acid, there is a strange smell. For example, acetic acid is vinegar. And even with the 5 or 3% that we have in our homes, if you open that up, if you open the bottle up and smell it, it's pungent. Okay, and so almost all acids are going to smell like that. Butyric acid is the one that comes from butter, hence the word butyric acid, 4-carbon structure. And so when butter goes bad, that's butyric acid. So here is a list of the physical properties, and again, this is just for your reference. You don't really have to memorize all of this, but it kind of gives you a good idea as to the boiling points of all these acids as they're increasing in the number of carbons. And also as you have more substituents on them, okay? And so solubility in water. Acidity we will talk about in a few minutes, okay? And so you can keep this chart handy. But anyhow, this is all the physical properties. And also you have the common names given in this chart, which is really handy. Okay, so acidity of carboxylic acids, the H of the carboxylic acid, the COOH. This is, of course, the acidic hydrogen, okay, and this is acidic because of the polar bond, again, between oxygen and hydrogen. And so if you treat it with even a weak base, okay, like sodium hydrogen carbonate, sodium bicarb, it will still react. Sodium hydroxide, yes, definitely, okay, but even with sodium bicarb, which is a weak base, it will still react with it and give a salt, okay? So this is a carboxylic acid salt. And what happens with this little reaction over here, it's a very simple reaction of an acid and a base to give salt and water, is that you completely change the properties of the carboxylic acid. Okay, so in some cases where carboxylic acid would be insoluble in water, we're not talking about the small ones, we're talking about the larger ones. But even if you were talking about the small ones, if they were not soluble in water, okay, they would suddenly be soluble in water because now they are acid salts. The other thing that happens is that here all the bonds are ionic, okay, and this is true for all carboxylic acids. Once they form salts, now there is an ionic bond, and because of this, they are now solids, okay, and because they're solids, they now have melting points instead of boiling points, okay, because all the carboxylic acids would be liquids. A lot of them are, okay, but then as the molecular weight increases, they turn into solids. So for example, benzoic acid is a solid, acetic acid is a liquid, but the salt of acetic acid, like sodium acetate or something, is going to be a solid because now it's got ionic bonds in it, okay, and so the properties are completely changed. And the nice thing about all these reactions is they are reversible, so which means that you can go ahead and protonate the carboxylic acid salt. All you have to do is just treat it with a little acid and it goes right back to the carboxylic acid. So it's a neat little reaction, and of course very good in changing properties. So there's a little bit different system for nomenclature of salts. You would name the salt as you would name the ionic salt, okay, which means that you name the metal first. So for example, when I said about sodium acetate, so sodium is the metal that comes first, and then the acetate, which is the carboxylic acid part. So you have to end in ate then, okay, in those cases. So benzoic acid will then end in benzoate, and then of course you have the sodium here in this reaction. So sodium benzoate. So anything, whether it is propionic acid, or propanoic acid, if it's propanoic acid, it would be propanoate, methanoate, ethanoate, so on and so forth, okay, and so you end everything in ate, and the metal is named first, just like ionic salts. Now, regarding the strength of the acids, okay, because they are acids anyhow, but how do they compare across the board? So here is the pKa's of alcohol, phenol, and then acid here, and then of course HCl is the mineral acid. So alcohols have a high pKa of 16. Phenols are stronger acids than alcohols because we talked about resonance, remember? And so this hydrogen here is more acidic than the hydrogen in an aliphatic alcohol. Then the pKa of a carboxylic acid hydrogen is 4.76, which is fairly strong acid. It's not as strong as a mineral acid though. Okay, so hydrochloric acid, for example, is -7, and sulfuric acid would be even smaller than that. But anyhow, so that's how carboxylic acids fall as far as the acidity is concerned. You can also increase the acidity of carboxylic acid by having groups on it that provide for inductive effect. Meaning that you can have groups that can withdraw electrons or donate electrons. So if you want to increase the strength of your acid, you can add groups that actually withdraw electrons, and if they withdraw electrons, they make the oxygen-hydrogen bond weaker. Okay, so for example, if you have any kind of fluorine or chlorine elements on the carbon next to the carboxylic acid functional group, then you can increase the acidity. All right, so here is OH on the carbon next to the carboxylic acid, and you can see a 1-point drop on the pKa level. Okay, and the same thing happens, actually worse happens, when you have 3 fluorine groups, because fluorine groups are so highly electronegative that they are 3 times more, and so therefore the pKa drops to even below 1, which makes trifluoroacetic acid a very strong acid. Okay, it almost borderlines the mineral acids now, okay, with the pK level. And a lot of times what happens in organic chemistry labs is that if we don't want to use a mineral acid, because if you use a mineral acid, you have to use water. All mineral acids are made in water. So if you don't want to use a mineral acid, you end up using trifluoroacetic acid because it's a fairly strong acid. Okay, so this is how inductive effect also affects the acidity of carboxylic acids. And here are the pKa's if you have any kind of substituent on benzoic acid. Okay, and so remember benzoic acid is also an acid, and in this case, since you have an aromatic ring, you can have substituents on the aromatic ring. So again, this little chart here gives you a good idea of what kind of groups you can have and what happens to the pKa, all right, of the acid. So nitro groups are of course very electron withdrawing groups, and so the pK is lowered, whereas CH3 alkyl groups or alcohol groups are very electron donating, and so the pKa is higher, okay, for those. So that's how you can change the acidity of a carboxylic acid on a benzene ring, so for benzoic acid, that is. Let's talk a little bit about the applications of carboxylic acids now. And there's so many applications of carboxylic acids. I only have a few over here for you, so you get an idea of how carboxylic acids are completely in our lives. Okay, and so for example, you can find a lot of the carboxylic acids in fruit juices. For example, all the citrus fruits, okay, that we have, grapefruit, orange juice, all of those, you will find citric acid in there. So that's carboxylic acid. You also find carboxylic acid as a product of fermentation. For example, vinegar. Vinegar, of course, we cannot live without vinegar. It's cheap, it's good, and it's so useful for so many things, all right? We talked about fermentation of butter before, and I mentioned to you that you can get butyric acid from the fermentation of butter, which really is not called fermentation, it's called rancid, okay? That something has gone rancid, meaning bad, and so butyric acid doesn't really have much function, okay? But vinegar, of course, is something else. A number of fats are also found as fatty acids, okay, which could be saturated or unsaturated. Remember, we eat fatty acids. All the oils that we have, those are all fatty acids. They're not just hydrocarbons, okay? So here are some examples of fatty acids. Now you can find them in vegetable oil or peanut oil, olive oil, all of these different kinds of oils. You find all fatty acids in there. So you have this whole long chain, which is the non-polar part of it, and then you have, of course, the acid component in there. So almost all of them will be monoacids. And then depending on what kind of a fatty acid you're talking about, the saturated ones are like this with completely like alkane, and the unsaturated ones can have double bonds, or they can have two, or they can have three, or you can have alkyne groups as well. So fatty acids are really essential for us. I don't think French fries would taste the same if they were not fried. And then, of course, we have the omega acids, which are really gaining popularity now because they're supposed to be good for you. And look at this, okay, there's so much unsaturation, okay, in all of these omega acids. And unsaturated fatty acids are considered to be better for us health-wise than saturated fatty acids. And we can talk about this in class also, but it also has to do with the type of double bond that you have, whether it's a cis or a trans. So it's not just a matter of saturated versus unsaturated, it's also a matter of trans and cis, okay? And then of course you know that trans fatty acids are not good for us. Cis then of course are good for us, all right? So these over here, all the omega acids, if you look at this, these are all cis bonds, all right? So cis are supposed to be good for us. Fatty acids are required by our body. It's not that you have an option for not eating fat, okay? You have to eat fat because the fatty acids are required for building the cell wall in our body. So if you don't eat fatty acids, then you will not be able to make cells, all right? And the first place where you see this happening is on your face, okay? And which is when your skin or starts degrading a little bit, you start getting wrinkles, your skin starts to break down. That is a lack of fatty acids in there. So, and they also provide insulation to our body and of course energy. Okay, so they're the second source of energy. The first source of energy is carbohydrates. So the second source of energy for our body is fatty acids. Okay, and so they're really important in our body. They're stored as triglycerides in our body, and triglyceride, we will talk about this when we get to esters also later on. But if you have three carboxylic acids like this or three fatty acids like this, they will react with one molecule of a triol. Triol like glycerol, okay, and then they will form what we call a triglycerides, okay. And you know that when you go for a health checkup, the one thing that a doctor will check for you is your triglycerides because too much of it is not good. And one of the other applications of ester of carboxylic acids is in polymers. The kind of polymers they form is what we call condensation polymers. Condensation polymers are when you take two molecules, combine them together so they form a polymer as well as a small molecule like water, carbon dioxide, HCl, something like that. Okay, so those are called condensation polymers. Anyhow, there are three kinds of condensation polymers that you form with acids. One is polyesters, the other one is peptides, and the third one is polyamides. Okay, polyesters, God knows what we will do without polyesters anymore. Okay, because that is how we make our fabric these days. Okay, or our clothes are made of polyesters. Cotton, of course, is a natural polymer, but polyesters are synthetic fibers. What you need is a diacid and you need a dialcohol. Okay, and they give polyesters. Remember, this is an ester. Ester is made from an acid and an alcohol. And we'll talk about all these functional groups later on also, but this is a good introduction for that part anyway. So here is the ester part here. This part here, the ethylene, this would be where the alcohol would be. Okay, so this would be the OH, this would be the OH over here. So this would be ethylene glycol or ethane diol, 1,2-ethane diol. And then of course you have the ester groups on both sides. You will need a diacid and a diol so you can keep the chain going. If you only have one and one of each, then you just form one ester. But if you have the diacid and the dialcohol on both sides, then the chain can keep going. This polymer that I've shown you here is terephthalate, and terephthalate actually is one of the bad polymers that's getting a really bad rap these days because of its toxicity. Okay, and so they're requiring all sorts of bottles not to have any of the terephthalates in them. Okay, but otherwise polyesters are really good as far as fabric is concerned. Peptides, what will we do without peptides? Okay, peptides are of course proteins, okay, and proteins are formed when you have two amino acids combining, all right, and of course this is what we find in our body to give proteins and all sorts of enzymes. A lot of the work that our body does is through proteins. So here's what happens. Here you have a whole bunch of amino acids. Amino acids have a main group in them and they also have an acid in them. Okay, again you need two functional groups on both sides so that the reaction can go on and on and on and on. Okay, so you can form polymers this way. So here is the link forming again. When you have condensation polymer, you will remove water. So this is the water that is being removed, and then you form this linkage over here as a result of removing that water, which is an amide linkage. An amide linkage in proteins is called a peptide linkage. Okay, it's just very specific, okay, to protein. So it's called a peptide linkage because amide linkage could be anything, all right? So in proteins, it's peptide. Anyhow, that is how proteins are formed, which is also a polymer. These are going to be natural polymers, of course. And then we have polyamides. Okay, and polyamides are really awesome because, of course, they gave us nylon, which is one of the strongest fibers, okay, out there. So there's a good history that goes with nylon. Okay, ask me in class. There's a good history of this. But anyhow, here we have a diacid and here we have a diamine, and we get this kind of an amide linkage. Again, remember this is an amide linkage because this is a polyamide. You have the amide linkage here also in peptides, but again, this is because it's in proteins. Because of amino acids, it's called peptide, and here we just call it an amide linkage. Okay, so this one specifically is called a 6,6 nylon because in each of the fragments of the amine and the acid, we have 6 carbons. Okay, and so this is nylon 6,6. But anyhow, nylon has a very interesting history. So for the key concept for this little portion of carboxylic acid, please know the nomenclature, know the physical properties with the solubility and boiling points and all that, and of course the acidity. I will definitely ask you to compare acidity across the board for different functional groups and also within carboxylic acids.